Good afternoon and welcome to Chemistry A, Unit 1, Atomic Theory, Day 4. Today we're going to talk about nuclear chemistry. We're going to talk about half-life. We're going to talk about the difference between chemical reactions and nuclear reactions, and about radioisotopes and topics such as that. So first of all, let's talk about what the nuclear atom is. The nuclear atom is held together by a force called a nuclear force. We also call this force the strong force. The strong force is an attractive force that acts between all nuclear particles such as protons and neutrons in the nucleus. Now remember, like charges repel and opposite charges attract. Inside the nucleus you have the positive protons attracting the negative electrons. Okay. Now, in this nuclear atom, you would think that the protons would push away from each other in the center of the nucleus, because as I just stated, and as you know, like charges push away on each other. So inside the nucleus of the atom, which we've already learned is the center, these protons are tightly packed with the neutrons. They should blow up, so something does not seem to be right logically. Well, that is because there is this thing called a strong force. Okay, the strong force is that force that dominates over the electromagnetic repulsions and holds the nucleus together. So in other words, the protons that are pushing away on each other, that are pushing apart because they are like charges, that force is not as strong as this nuclear force or strong force, which holds the nucleus together and therefore holds the atoms together. Okay? Now let's talk about what a nuclear reaction is. There are over 1,500 different nuclei discovered, and of those 1,500 nuclei that are discovered, only 214 are stable. Stability basically means that they will not decay over time, or they will not change over time. Okay? That's what decaying is. We know decaying as something that's breaking apart. Decaying when it comes to nuclear reactions we're talking about these nuclei, and they break apart or they change over time. Okay? What causes stability? How am I going to know if something is stable or not stable? It's all based on a neutron to proton, ignore the spelling, neutron to proton ratio. Remember what a ratio is. It's a comparison of one item to another item. For every 2 hydrogens, we have 1 oxygen. That is a ratio. Okay? Now, radioactive isotopes are basically unstable isotopes. That's all they are. So everything that is an unstable isotope is called radioactive. It's a radioactive isotope. All right. Well, what is the difference between a nuclear reaction and a chemical reaction? Well, remember, a chemical reaction, there are 2 or more things combined to form something new. However, they don't lose their identity. Hydrogen and oxygen, when combined chemically, form H2O. But we can still see hydrogen and we can still see the oxygen. Chemical reactions involve atoms tending to gain stability by losing or gaining electrons. Okay? Mass is conserved. In other words, mass is neither created nor destroyed by ordinary means. That is what the law of conservation of mass is. So in chemical reactions, electrons are either shared or lost, gained or lost between these atoms, and that is what causes stability. So when you see baking soda react with vinegar and it causes a reaction where gas is produced and you see bubbles and you see it overflow and then it settles down, when it settles down because stability has occurred. Okay? Mass being conserved means that in other words, this means that if the mass of the ingredients in the recipe is 55, when the recipe is all done, the mass will still be 55. Okay? That's what the law of conservation of mass means. Nuclear reactions, though, are unstable isotopes, the nuclei of unstable isotopes called radioisotopes, gain stability by changing. The changes give off large amounts of energy. Okay? So nuclear reactions, change actually takes place where the mass changes. Mass is lost. All right? And this change gives off tremendous amounts of energy. Okay? Mass is not conserved, means it's lost. And the mass defect is a measure of how much decay takes place. And generally, in any reaction, small amounts of decay are taking place. Okay, well, what is something called half-life? All right, all half-life is a measure of the rate of decay. The textbook definition of half-life is the time required for 1/2 of the nuclei of a radioisotope to decay to products. After each half-life, 1/2 of the existing radioactive atoms have decayed into atoms of a new element. Let's take a look here at the decay of carbon-14. As you can see, at the beginning, which is called 100%, there are 10 grams of carbon-14. One half-life is the time that it takes for 1/2 of the existing radioactive atoms to decay. So as you can see, it takes 1 half-life for it to go from 10 carbons down to 5. 1/2 of 10 is 5. And another half-life is the time that it takes for it to go from 5 grams to 2.5 grams. And from 2.5 grams down to 1.25 grams. Each half-life is the time that it takes for it to lose the existing half of the particles. And eventually this will go away into almost zero. Okay? So the number of half-lives for carbon-14, each half-life takes 5,730 years. This can be a very quick, instantaneous half-life, or like carbon, it can take a long time. Okay? Examples of forensic scientists use half-life to determine how much or how long a drug has been in the system of somebody who maybe has passed away or has been sick or something along those lines. If you ever watch CSI or those kinds of programs, you'll notice they're talking about, well, there was this amount of chemical left in their body. Estimate that there may be a few hours ago was the death, or whatever they're trying to determine when the person was shot or the incident occurred. So forensic scientists use half-life all the time. So half-life of some of the common drugs that we are associated with or we know about are caffeine. The half-life of a caffeine is 4.9 hours. So it takes 4.9 hours for 1/2 of the caffeine in your body to leave your body. It takes 0.25 hours of aspirin. For every 0.25, you lose half of the aspirin that you're taking. That's why you can take those much quicker than some of the other drugs. Nicotine, half of the nicotine will leave your body in a 2-hour time. This is why people who are addicted to nicotine have to go out and have cigarettes. Okay? So scientists also will use carbon-14 for age dating. This is all based on half-life and the decay rates. Why do we use this? We use this because the ratio of carbon-14 to other isotopes is fairly constant. Okay, at this point we want to take an opportunity to take a look at some of the half-life calculations that we can do. So please, for tomorrow, take a look at page 806, the sample problem. Please read the sample problem dealing with carbon-14, and we will discuss that sample problem, and then we will go over sample problem number 7 and number 8 in class. But I definitely need you to read that sample problem 25.1 on page 806.